Yeah, roughly, yeah, sure, it's no problem at all. I just never like to be late, so I will also turn on my thing here. Yeah, you can start right now.
Okay, so good afternoon. So we'll start the next session. The session has two talks. The first talk will be delivered Professor Rahul Pandit, and he will tell us about self-gravitating bosonic and exonic systems and pulsar glitches.
I would like to begin by thanking the organizers for inviting me for this wonderful meeting. And I will talk today about something which looks like it's not statistical mechanics, but it really is between astrophysics and statistical mechanics, which are two of the strong areas in this institute, so I thought I would talk about it. But before I do that, let me add my best wishes to those of everyone. I mean, this institute has trained and nurtured and inspired several generations of students and physicists all over the country. So thank you again, and many happy returns. This work which I'm going to talk about has been done with Akhilesh when he was a graduate student with my group, is now in Miami, Sanjay, who's in the audience, who can answer all the questions, and Marc Brachet, who's at the École Normale in Paris. And I'd like to acknowledge funding from all these bodies. Here's an outline of my talk, a motivation which might have been redundant had it been a fully astrophysics audience, but I'll give you some. Then a discussion of the equations that I will use, the Gross-Pitaevsky-Poisson equation, and the equation, the same one with a crust, then some direct numerical simulations, results, and conclusions. So here are dark matter pioneers. Actually, there's a beautiful article, not too old, which traces the history of dark matter. It actually goes back to some dark bodies discussed by Kelvin and Matière Obscure of Poincaré. But modern quasi-history sort of begins with Zwicky, who talked of Dunkel Materie, which he first surmised from the virial theorem. And of course, then the celebrated work of Rubin and Ford, who showed that there's a discrepancy between the predicted angular motion of galaxies and the observed motion of studying galactic rotation curves. And this became known as the galaxy rotation problem. So, this dark matter plays a central role in our understanding of modern cosmology, according to this historical review. And cosmological measurements show that about 85% of the matter in the universe is non-baryonic, cold, dark matter. Okay? And of course, there's been a lot of macroscopic evidence of the existence of dark matter, but we still have not been able to identify, because in spite of several excellent experiments, what is the nature of dark matter, and that remains a major challenge in this field. There are lots of recent references which I've been giving there. Now, Okay, this summarizes just what I said, that, you know, there have been lots and lots of searches, but nothing definitive yet. And in this same meeting, which was in 2017, no new smoking gun. All right. In the old days, people talked of baryonic dark matter, and they love acronyms, so they call them massive astrophysical compact halo objects, namely MACHOs. Okay, they were never found. Of course, the most revolutionary suggestion is modified Newtonian dynamics. You just have to modify Newton, and you don't have to worry about dark matter. Okay, they keep on, you know, making it more and more sophisticated, so as an outsider I can't tell. The leading candidates were something called weakly interacting massive particles, called WIMPs. But even they haven't been found, and the title of this article tells you where it stands at the moment, at least in 2018. And then among the candidates whose consequences I will explore in this talk are axions, which are basically things which arise from an unrelated problem, unrelated to the present talk, the strong CP problem. These people suggested that they should introduce a new global U1 symmetry that should be spontaneously broken, and then other distinguished physicists realized that there should be some Nambu-Goldstone boson, and they called it an axion. So this is one of the dark matter candidates, and there are many searches for it. It has still not been found, but it's a candidate. So while we wait for our colleagues to find these candidates, whichever one is the correct one, it behooves us to study systems which are bosonic and axionic to see whether we can look at models in which they appear either as candidates for dark matter halos or compact bosonic stars or axionic stars. And this is what I will cover in my talk today. The first topic we published not too far back in time is the formation of compact objects at finite temperatures in a self-gravitating bosonic system. So here this should remind you of statistical physics. We are talking of a superfluid state. So we will describe that weakly interacting Bose gas by this complex wave function, the Gross-Pitaevsky equation. Forget Poisson for the moment. So psi cubed, basically. Now, if you have Newtonian gravity, and I will not be relativistic in this talk, then you can put in the gravitational potential things are suitably dimensionalized. So this G, capital G is the strength of gravity, little g is the strength of the interactions between the bosons, and this phi must satisfy this equation, where the mean value of mod psi squared is subtracted off. In the absence of gravity, there is a sound wave, and that's the speed of sound. And you can also get a coherence length out of it, which would give you the coherence length for, say, a vortex core or something. How do we study these? We study these by, superficially just direct numerical simulations of the pseudospectral sort, but with a lot of clever algorithms, which I will just indicate as I go along without getting into details. So that's the Fourier pseudospectral thing. Early work on this in Mark Brachet's group, along with Giorgio Krustulovic for the 3D case, and 2D case, my student Vishwanath Shukla, now at IIT Kharagpur, and Mark Brachet and I for the 2D case. So the basic message is the following. You take these equations, you put them on a computer, you're using a pseudospectral method, then you keep a finite number of Fourier modes. When you do that, basically you have a microcanonical evolution of those modes. And that's at fixed energy if you've truncated things properly. So eventually it thermalizes. When it finally thermalizes, of course, it is not describing the partial differential equation to start it with. But for a long range of parameters, it does have enough spectral resolution that you can. And so we use this method to study finite temperature effects in this thing. For example, in the old days when we studied this problem in 2 dimensions with Vishwanath Shukla and Marc Brachet, we found, for example, that there are initial transients that depend on initial conditions for this Fourier truncated Gross-Pitaevsky equation. This is without Poisson. Then there was an onset of the thermalization. Energy and occupation number spectra began to show power law scaling with power law exponents that depend on the initial conditions. Then there is partial thermalization. Spectra show clear power law exponents that are independent of the initial conditions. In particular, in 2D, I think the energy should go as K. And indeed, we pushed it far enough that we could get the Berezinski-Kostless-Thouless transition out of such a simulation, which is not easy to do. Okay, now if you have gravity, then you can linearize this GPPE for short, about a constant wave function psi squared equal to n0, and you get the following dispersion relation. And this displays a low K Jeans instability, very famous in astrophysics, which says that for wave numbers smaller than this Jeans wave number, there will be an instability, and the state will collapse. So here's the equation again. Let me show you how we study it. So we Fourier truncate, periodic boundary conditions. You have to be clever, have everything momentum conserving and good time marching, etc. When you do this properly, the number of particles is conserved. The momentum is also conserved with suitable de-aliasing for those of you who are experts in direct numerical simulations. And the total energy is also conserved, which consists of this gravitational part, the interaction part, and this quantum kinetic part. So again, just as I mentioned very quickly, in the Gross-Pitaevsky case, we get the spectral truncation, and therefore we can study finite temperature effects. Similarly, in this Gross-Pitaevsky-Poisson case, we can also get finite temperature effects. Now, if you just follow the Gross-Pitaevsky-Poisson equations, it will take you a long time, or take the system a long time, to get to the correct state at that temperature. So it is advantageous to use you perform, if you like, a Wick rotation. You go to imaginary time, and you get a stochastic Ginzburg-Landau-Poisson equation, which we can even put some noise. So this is P sub G is the Galerkin projector, and all the other symbols have their standard meanings. So there's a chemical potential. You tune the chemical potential to conserve the total particle number. There's the temperature, and there's the Gaussian white noise. And it turns out that when you use the stochastic Ginzburg-Landau treatment, you reach the equilibrium state faster than you would otherwise. So it's a numerical trick. The dynamics of the stochastic Ginzburg-Landau-Poisson equation has no real meaning. It's only the Gross-Pitaevsky. So for example, we can start with some initial condition and then see whether we get gravitational collapse. And okay, I've given them all, so let's not worry about the details. You can work in certain limits where you neglect various terms. And then this was done especially in the group of Chavanis in France. Here's the energy as a function of R, interaction term, gravitational term. This is the that other quantum pressure term. And in the non-interacting limit, I probably forgot to say, A is the scattering length scale. So the strength of G is dictated by A. You get some length scale. You can also use a so-called Thomas-Fermi approximation in which the quantum energy correction vanishes. You get another scale. These are the references to the papers by Chavanis. Similarly, you can extract masses. Okay, that's a mass. And here is a length. and that's an energy. I bring all this up because we just non-dimensionalize all the quantities that I will tell you about in terms of these natural scales. So here you could find the ground state radius of the collapsed object at the level of these approximations. And in any calculation, you can find the radius of gyration of the collapsed object by using this formula. Now, okay, here is the non-dimensionalization that I was mentioning. So, you can non-dimensionalize by the scattering length or these radii and so on. You don't have to worry about the details for this talk, especially if you're not a real astrophysicist. So these are lots of runs. I won't go over all of them, but I will show you some representative runs. So if you start, this is the stochastic Ginzburg-Landau-Poisson equation. You start with this initial condition, and it collapses very rapidly. That's really a spherical object with periodic boundary conditions. Okay, so that's how it collapses, and it does it fairly rapidly on the scale of these simulations. Now you can ask what happens to the radius. The radius, as a function of time, it eventually goes to that value. You can ask what happens if I do it fully Gross-Pitaevsky-Poisson, not this artificial stochastic Ginzburg-Landau. Let me see whether this movie works or it doesn't work. Okay, it does work. Okay, so this is the Gross-Pitaevsky way of doing things. And fine. The question is, do you get to the same radius or not? Now, what my claim is that actually, if you look at these graphs carefully, which I don't expect you to do in such a short talk, by suitably choosing the temperature of the stochastic Ginzburg-Landau-Poisson equation, we can get the same large time radius for this case, okay? And you can do bigger system sizes and so on. This is the stochastic Ginzburg-Landau-Poisson, but at a finite temperature. What I showed you earlier was at zero temperature. So here you can see that you get a spherical object with suitable periodic boundary conditions, but because of thermal fluctuations, you get a fluctuating object. Okay, and all right, this is the radius. And this is what I just said, that if you look at these details, then the final states of the Gross-Pitaevsky-Poisson and the stochastic Ginzburg-Landau-Poisson are the same if you tune parameters properly, except that the stochastic Ginzburg-Landau-Poisson gets there faster. Okay, you can also get more complicated states. I mean, if you look, you can get a completely shredded object if you are at higher temperatures, which is not surprising in itself. Okay?
So
yes?
So the final radius is just determined by pressure balance and gravitation?
Yeah, it's all in the equations. Now I don't have to do any, it's all there. There's quantum pressure.
But it's just the quantum pressure?
Yes, exactly, right. I mean, I didn't write it at the level of the Hamiltonian. I could have. I took the derivative of it, so that's why it was a cubic, but that would be a quartic term in the interaction in the Hamiltonian, if you like.
Is there evidence that this dark matter is a quantum phenomenon, or is it just
Well, the honest answer is nobody knows, and we are trying everything. If it turns out to be axions or bosons, then these calculations will be relevant.
is there a classical limit of such a Poisson?
I mean, you can do the Thomas Fermi analog, and that Chavanis has done, and you get a spherical object, but without any fluctuations. Okay? All right, you can measure many things and compare them against what has been done analytically by the Chavanis group. You can measure radius as a function of scattering strength and all that. And various things work out, and various things are interesting. But let me show you one thing which was not appreciated at all until we did this work, which is now I can follow the radius of this collapsed object, the radius of gyration, as a function of temperature. And if you do that, you get a hysteresis loop. Okay, so that's the forward trace and that's the backward trace, and this hysteresis loop is a signature of a first order transition. The transition is from a condensed object, which of course is a Bose-Einstein condensate, to a tenuous object, and this is driven by temperature. Later I will show you such a transition driven by gravity also. You can ask, is this single collapsed object the only thing which you can get? The answer is no. You can do better, I mean better or different at least. You can get a binary star system with suitable initial conditions, which I'm not going to explain now, but take my word for it. We can get from this Gross-Pitaevsky-Poisson, we can get a binary star. Okay, if you like. If you want to call it a binary star, you can call it a binary object, whatever you like, and it goes round and round. Okay, so I think the first message is that this Gross-Pitaevsky-Poisson system is a good system in which to study such a collapsed bosonic object, and we can do it at finite temperatures. Earlier studies were all at 0 temperature, and you know, there is a thermally driven first order phase transition which was never seen before, and it should be contrasted with the continuous transition. You get a Bose-Einstein condensate in a weakly interacting Bose gas, which is described by just the Gross-Pitaevsky equation. And we can also get rotating binary stars. So let's move to axions. I mean, there is, again, the whole articles and reviews of modern physics on the physics of axion stars. At a practical level, for our description, we need to concentrate on this, that there's a negative scattering length A. Therefore, in the model that I wrote down, where little g was the interaction, little g will be negative. And all of you who know critical phenomena know that that will lead to an instability. And when that, we do it all the time when we study tricritical points. So when that term goes negative, then we have to add a higher order term, which is what we have done in this paper, which we have just submitted for publication. So here's the new term. So at the level of the equation, it's a quintic term. All right, in a Hamiltonian or something, it would be a 6th order. So that's, yes?
Do you take the next order term also?
No, we do with as small a set of things as we can. Of course.
Is the sign of the coefficient?
No, not really. This is enough to give us everything. So G2 is positive, G is negative. So this is the so-called cubic quintic, Gross-Pitaevsky-Poisson. So now all of you are experts in this, so I don't need to describe all the details. Again, suitable particle number conservation, energy conservation. In the absence of gravity, you can work out the speed of sound, you can get the coherence length, and so on. And again, you do this Galerkin projection onto a finite set of states in Fourier space. And this is what the truncated equation looks like. These things are conserved. And again, we study the formation of structures starting from a nearly uniform density, and we can also write down a suitable stochastic Ginzburg-Landau. I didn't write that properly. That should be S, so CQ-SGLP, cubic quintic. All right? And we can also study, let me introduce rotation here, that if we want to study rotating stars, then we can add a rotation term here in addition to all these terms, omega Lz, where Lz is the z component of the angular momentum. Okay? This will come in handy when I go to the last part of my talk. All right, so first thing, let's look at the radius of gyration as a function of the gravitational strength. And this time, this is at 0 temperature, but we have a sequence of first order transitions. As you expect, when you increase the gravitational strength, the system will collapse, but it does so in a very interesting way. Here's the disordered states at low gravity. Then you get these sheets, which might be metastable, but they last for very long. And it is tempting to speculate that these are what in the astrophysics literature have been called Zeldovich pancakes. Then it goes to a cylindrical structure, and finally to a spherical structure. And again, if you go scan back and forth in G, you get a sequence of hysteresis loops, each associated with a first-order transition of this sort. That's the forward trace, and that's the backward trace. And these insets show you the nature of the collapsed object. Now, do you get transitions as a function of the other parameters in the problem? The answer is yes. So let's stick to 0 temperature, but with fixed gravitational strength. And here, you might not be able to see it. On the horizontal axis, I have G2. That was the coefficient of the cubic quintic term. Okay, and this is the radius of gyration. And you get the sequence of first-order transitions, which show up here as hysteresis loops. And here, you see it as a function of temperature. Here, the hysteresis loops are not so clean, but they're there. And there are probably not as many of them, but there probably are. This might be a very narrow one. Okay? So we can get these as thermally driven hysteresis loops. So I've shown you both gravity and thermally driven hysteresis loops in this model. So here I said that we can put in rotation, and you can see that as you put in rotation, as you might expect from your knowledge of condensed matter physics, that you will get vortices beyond some critical rotation rate. And you see that as you increase omega, there are no vortices here. Some vortices start at omega equal to 4, and omega equal to 5. It starts rotating, and more vortices come in. And you can find the critical omega required for these vortices as a function of the interaction strength G2, and it goes down as G2 goes up. And if you want to see what it looks like, I mean, this is what it looks like. This is for the case omega equal to 5, and you see the vortices threading the collapsed object. Okay? All right, so can you also get a rotating binary? The answer is yes. And you can, get lots of different answers. So here is one sort of initial condition that people try. There is an e to the I v1 dot x, and then there is a phase in between. And the type of rotating objects you get depend on the phase. I won't go through all the details in this short talk. But here, you can see some of the types of rotating objects, which might not be clear in the picture, but at least let me show you one. You see how these things come together, and they actually bounce back and forth. Eventually, with these parameter sets, it will probably collapse into one object. But before it does that, it does a lot of interesting things, which I'm sorry, the movie is too short to show you everything. So you might worry about units. I've been, proceeding like a pure theoretical physicist, working with h bar equal to 1, m equal to 1, and so on. But let me say that if you were considering dark matter halos, then you think of ultralight axions of that sort of mass. And if you put in length and time scales, then our simulation box is roughly 2 pi cubed kiloparsec cubed. Okay, 2 pi, whatever, kiloparsecs cubed. Okay, and the time step delta t in our simulation would be 4.8 years. But if you're thinking of an axionic star and you put in that sort of mass, then the box size is kilometers cubed, and the dt is of order microseconds. So it really makes a big difference. But the framework is there. You pick your favorite axionic system, and then we can put in the units for you. So again, we have presented a complete first principles computational study, which includes thermal effects of studying collapsed axionic objects. It's a superfluid, of course, the collapsed object. And our study, again, goes well beyond earlier studies, which typically stop at Thomas Fermi and are 0 temperature. And, okay, I've said everything, that you can get both thermally driven and gravitationally driven first-order transitions in this thing, and you can also get rotating binary axionic stars. So let me now go to pulsar glitches. Pulsar glitches are intimately related to this institute because Sanjeev told us that Professor Radhakrishnan, he was the director of this institute for several years, and before he came here, in this very important paper written in 1969, he was at CSIRO in Australia. He and Manchester, and at the same time Reichley and Downs, found something called pulsar glitches. I will tell you what about. Okay, by the way, I gave a first talk on pulsars in this room in 1976. And okay, he was in the audience also. But that was a master's project. We had a summer school, you know, and I was a young student. Okay, so here is the plot taken from the paper of Radhakrishnan and Manchester. So this is date of observation. You can't see it very well. And this is the period. And suddenly, the period goes up, okay? And this sudden spikes in the period, which were measured in 1969, go under the name of pulsar glitches. So a modern written by Manchester in 2018, okay, this was in the Vela pulsar, and in 2 different labs at different parts of the world, they found that there was this increase. So there have been many such studies over the years. And now these glitches have been studied for many different pulsars. Okay, to a first approximation, I mean, what's a pulsar? A pulsar is a rotating neutron star. Okay, so the first approximation, these people and some other groups have suggested that, look, it's just neutron Cooper pairs. They comprise the major component of nuclear matter in a pulsar, and they form a superfluid. Okay? Well, what can we do? Some people studied this along with a crust potential as a very simple model for pulsar glitches. But their Gross-Pidaevsky system was held together by a confining potential. Okay? But of course, you must have gravity. So nobody had put in gravitational effects into this, and this is what we have done to produce a minimal self-gravitating model for pulsar glitches. We use the Gross-Pidaevsky-Poisson equation, and we include rotation. I've already shown you how we include rotation. And in addition, we include an interacting solid crust. So this is the paper in which we did this. It appeared quite recently. So it's a rotating, self-gravitating Bose-Einstein condensate. And in addition, it has a crust. And as I will show you, it's a very simple model for pulsar glitches. Okay, so we have already shown in the absence of the crust potential that if you rotate such a bosonic star, it is threaded by vortices. I showed it to you for the axionic star, but it goes through in the same way for the bosonic star. The interaction of these vortices with the crust potential yields a sort of stick-slip dynamics. Also dynamical glitches, as I will show you in a few minutes. Now, if enough angular momentum is transferred to the crust from the bosonic star, then the vortices are expelled from the star. I will show you movies, so it's not all words. And the crust's angular momentum, J sub c, exhibits features that may be interpreted as glitches. At least in this model, they are the glitches. And from the time series of J sub c, we compute the cumulative probability distributions of event sizes, event durations, and waiting times, which I will define precisely in a few minutes. And we show from these CPDFs that they have the signatures of self-organized criticality, which are similar to those that have been seen in observations on pulsar glitches. So SOC is another link with statistical physics, which justifies my talking about this subject here. So here is again Gross-Pidaevsky-Poisson, but with a new term called V sub theta, which I will define in a few minutes. Again, everything else you know before from what I have told you. So the simple approximation is that we can describe the dynamics of a crust by one single polar angle, which evolves in this way. So that's the moment of inertia of the crust, and that's theta double dot. And that's the crust potential, which I will define in a minute. And then there's some friction. So I'm putting in some friction by hand, minus alpha theta dot. The crust potential is parametrized as follows. Okay? So alpha is controlling the friction. IC over alpha square root gives you a friction time. For simplicity, we just parameterize this dependence on x theta, y theta in this way. So n crust determines, if you like, the number of pinning sites in the crust potential. R crust is the radius at which this v theta has a maximum. And delta R crust determines the thickness of the crust. So these are the parameters in the model. Okay, fine, sure, no problem. Now we use periodic boundary conditions, so those of you who are real formalists will say, aha, then your angular momentum J sub z will not be conserved. But we have a clever way of choosing it so that it's nearly conserved. Okay? I'm not going to describe all the details, they're all in the papers. But we define new variables, xp, yp, vp, and this is the pi center 2 pi periodic coordinates. And the crust will act on the GPP fluid just as the fluid acts back on the crust. Okay? So again, Fourier truncate and so on. These are the things which are conserved. In the absence of the crust potential and no friction, even the momentum is conserved if you do things properly, and all these energies are conserved. Okay, again, you can do it at finite temperature using a stochastic Ginzburg-Landau-Poisson equation along with a crust potential, okay, etc. I won't go through the details. And this time, you want to study it with a rotation. So the rotation term is here omega jz, where jz is the z component of the angular momentum. This is a functional derivative. Psi bar is the complex conjugate of psi. And when you go through all this, you get a complicated equation which we call advective real Ginzburg-Landau. Don't worry about the details. But when you solve for the rotational ground states, which are minima of E minus omega jz, you manage to get these vortices threading this object. By the way, this has never been found before because people didn't have this clever numerical scheme. It's a very nice, beautiful algorithm. So let me show you what the z component of the angular momentum looks like as a function of time. That's the red line. So it's not exactly constant. This is because of the square, the cubical box and periodic boundary conditions. Okay, so there is some loss because it's not really rotationally invariant. But you can look also at a plot of E minus omega jz versus omega. Again, there is some hysteresis. Forward, there are no vortices, and then suddenly a state with 4 vortices. You come back, and that's how you go back to the state with 0 vortices. So by rotating this object, we can get the vortices. Here are the vortices, shown with just nice surface here, and this is some other representation, curl of rho v whole squared. So you can see the vortices threading this object. Now, this is a more complicated plot. The blue isosurfaces show the crust potential. The red things which are popping through are the vortices. And this is as a function of time. Okay? At early times, you see 4, and then you see 3, and then perhaps 2, and then only 1. Okay? So this is doing what it is supposed to do. It is going out of the system. So if you plot J over JC0, JC0 is the initial crust potential. So if you plot it versus time, you see this really jagged structure, okay? Don't worry about conservation. It is good to 1% because of the effect I told you earlier. If you zoom into one of these things, you get a plot like this. All right? So you can ask, well, this is a very complicated structure. Does it have any statistics? And it is conventional in this trade to characterize the statistics by using the measures that I'm now going to define. So from the time series of JCT, we see that the crust can either lose or gain angular momentum to or from the superfluid because the vortices either stick to or slip from the crust. Okay? To characterize their statistical properties, we calculate the gain delta JC in the crust angular momentum between successive minima and maxima of JCT. And we call delta JC the event size. We can scale it with JC0. We also calculate the event duration time TED, the time difference between successive minima and maxima, and the waiting time, which is the time difference between two successive maxima. You can get various CPDFs. Let me just show you the event size one. This is a log-log plot. There is a straight line. So that's a power law. And at least in the regions that we have found, don't look at all the details, we get powers which are consistent with what are seen experimentally. There's a wide range experimentally. The exponents lie in some range here with this peculiar thing because it's cumulative. But our number lies in that ballpark. And there is one PDF, which is the waiting time PDF, which is an exponential. This is a semi-log plot. And such exponential PDFs are also seen in the experiments. So we have shown that you can have these rotating vortex-containing gravitationally bound solutions to the GPP with a crust. This is a natural but minimal model for self-gravitating objects which are bosonic, interact with a crust, and lead to stick-slip dynamics by including the crust as I have done. And you get SOC-type results which are in consonance with the measurements. Okay? So I thank you for your attention, and I'm happy to answer questions, but you can see this is the result of an even more complicated calculation that Sanjay is doing. He's at the back of the room, where we have both protons and neutrons. So the blue things are, vortices of the sort that we know for a superconductor, and the red are vortices that we see for a superfluid. So thank you very much for your attention.
So Rahul, so from this, so you showed the interacting bosons in the presence of gravitational interactions, right?
Yes.
And so I didn't quite understand how this sort of tells us something about dark matter, like.
No. You should read. I wrote it like a lawyer. If dark matter is eventually found to be made up of axions, if it is found to be made up of collapsed bosons, then our model is ready. Okay? So it's predicated on somebody someday finding this. Yes?
But in it,
That this is dark matter doesn't really play a role, right? It's just bosons.
Sure. But if it is, absolutely, that's true. But the astrophysical literature is full of things like dark matter halos, axionic stars, etc. So to the extent they talk about them, here we are showing how to compute with it, at least to the level of Newtonian gravity and good old condensed matter physics.
It would be weakly interacting.
Sorry?
It would be weakly interacting.
Uh,
Except for gravity.
except for gravity, yeah. Yeah, sure. Gravity is there. But Newtonian, haven't done relativity yet.
Any other questions?
Sorry, just slightly this thing. If I have just a 1D GPP, just in one dimension, Are anything known about soliton solutions for this kind of modified one?
I'm sure I don't know about GPPE. Of course, GPE is an industry.
Yeah, GPE is fine, but GPE.
So we should look, but again, I think in this particular case, 3D is important,
I see. So,
I think. Okay.
thanks.
Okay, thank you very much. Can you give me this? I go that side.
So our next speaker is Professor Vibhu Prasad, and he'll tell us about the Pemba effect of galvanic gases.
Oh, excuse me. I ran away with your microphone.
Hello. Hello. Hope I am audible. Hello. Yeah. Okay. So, good afternoon, everybody. I am Prasad, and I work at Cochin University of Science and Technology in Kerala. It's down south in India. And first of all, I would like to thank Sanjeev for giving this opportunity to present our work in front of this august audience, because I have learned a lot from many of the speakers here in the same audience, in the same auditorium, maybe 6-7 years back or more than that, as a student during the first versions of RRI schools. And also, I'm also happy to be part of this 75th anniversary of RRI as an alumnus. So I thank the organizers for that. Okay. So today I'll be talking about certain exploratory work that we have done in connection with the Pemba effect, which has gained certain recent interest in the scientific community, and in particular on the system of granular gases. So this is the outline of my talk. So initially I'll briefly introduce the Pemba effect and in the general context, it's the general ideas and phenomenology. And later I'll go to the context or Pemba effect, how it is sort of described in the context of granular systems. And finally, I'll look at certain considerations that one has to take in when we look at various distance measures that we employ when studying Pemba effect in granular systems. So that's the idea. Okay, so when did it all begin? So Pemba effect is mainly related to the how a system relaxes to a final steady state or final time invariant state when it starts evolving from an initial state. So it's about time evolution of system, and this question was not very recent, because such ideas were gained, or such ideas were there in the Aristotelian times itself, when it was sort of believed that if you want to freeze a beaker of water or volume of water, it is better to keep it under the sun for a while before, so that it gets frozen in a faster manner. So this was sort of a belief or lore that was there in those old, ancient times, but this was sort of counterintuitive when we look at from the modern perspective, and from the Newton's law, we know that the time evolution, or how does the temperature evolve as a function of time, and it follows this behavior, and it's a one-dimensional differential equation, and there can't be any crossing trajectories which is required to have a faster equilibration of a system. So from what Aristotelian thoughts, Aristotle was believing was that if a system is hotter, then it cools faster. So that requires a crossing of trajectories from a certain initial temperature, and that is not possible in terms of Newton's law. And that can be also seen from the solution that we can see here, that the time to equilibrate increases as a function of the increase in the temperature difference in the system. So according to Newton's theory, or Newton's law here, the cooler sample will cool sooner. Okay, so then how did this interest suddenly re-emerge? This was because of certain experiment, the school experiment that was done by Erasto Pemba and his PI, his sort of advisor, Osborne, who basically did a school experiment where what they tried to do is to take a small volume of water at 2 different temperatures, and they put this thing in a refrigerator and measured the time to freeze. And this is what they observed, one of the figures that we could see in this paper. And what they see is that for the time of freezing increases as we increase the, the initial temperature. So there is this negative slope that we see. This indicates that like it takes smaller time if you start your the cooling temperature to be high. But even they were also not very sure about this thing, and they know about the counterintuitive nature of this result, and they possibly hint at some convective sort of influences that affect this kind of results, and they also indicate for further, or they ask for further verification of these results. And people have indeed tried to examine this result closely, and what we can see here on the top are the 2 results that are sort of affirmative of this Pemba's observation that hotter sample cools faster, as we can see here in these 2 figures, these negative slopes. But this is not all. We could see in this figure several results, several experiments that people have conducted, and we could see like sort of 50-50 chance that it can be either way, because here you can see a monotonic increase in the cooling time as a function of temperature, higher temperature. And this red one is the Pemba's result, and you can see indefinite sort of observation that we cannot make any better observation from the other results. So this is the status that one could have one has for the Pemba effect when considering systems, aqueous systems. Now, but this kind of ideas actually gained increasing interest, and one could see that there were several other systems where this sort of dependence on initial state in the way the system cools down to certain final state occurs. We can see this in these different systems. Here you can see magnetoresistive alloys where the magnetization cools in a certain time-dependent manner, and this certain system with higher magnetization cools or relaxes faster compared to the other systems. And again, in carbon nanotube, there are certain resonant frequencies, and one tries to so the systems which are excited relaxes faster compared to the other ones. Excited at higher energies relaxes faster. And this is somewhat recent studies on colloids. Here also one can see, we'll see this in detail, but what one can see is that a hotter system cools exponentially faster compared to a warmer system to the final state here. So this is the context that we are looking at now, and we have several theoretical and numerical studies ranging in various systems where we could see such memory effects in the cooling. And what one can see is that typically the higher energy states cools faster in these systems. So this is where we want to head start, and actually the main interest started appearing from around this time when Liu and Ras. So these guys published a PNAS paper where they tried to understand this sort of behavior from a formal perspective by looking at a linear evolution of the probability distribution. And whenever there is such a linear evolution, so for example, let's take a finite state space system where one can see this evolution in the matrix representation, where these are basically the weights of jumping from one state to another. And if we are considering a system which is in connection with a thermal bath, then one can basically compute all the weights to jump from one state to another. And one can also calculate what is the time invariant state in the system. This is the equilibrium distribution for this system. And what one can do further is you can describe this evolution in terms of its eigenstates and ordered eigenvalues. And given this, we can explain we can calculate the evolution of the system from whatever initial states can be represented in this manner in terms of this eigenbasis and the time evolution in this manner. Now, given this sort of setup, we can show that the distance, the vectorial distance between evolution of a hotter system compared to a cooler system can be represented in this manner. And this leads to a condition: when can a hotter system reach to the final state in a faster manner? That leads to a condition saying that the coefficient A2, which is related to the initial state, so this A2 corresponds to the colder system, is greater than that corresponds to a hotter system. So if this is satisfied, one can argue that the cooler system or the hotter system approaches the final state in a faster manner. So this can be also been illustrated in this three-state system. And in the probability space, we can see this the red curve is the equilibrium contour. And from a hotter initial state, there is so we are quenching the system from a hotter initial state and a cooler initial state to this final state. And in the asymptotic regime, you can have the main evolution will be in terms of the A2 is 0, or subspace that A2 is 0, then the dominant contribution is coming from the next lower order relaxation. And then what happens is that you are basically going into this, along this subspace, and you can basically relax to this final state exponentially faster. So this can also be seen unrelated figure. So I won't go, I'll go to this model later, but this is sort of a typical picture of a exponentially faster relaxation compared to the typical relaxation in the system. And one can also see an inverse Pemba effect where what we are looking at is where if we want to cool, instead of cooling, we want to heat up a system, then what will happen, whether is it possible to heat it faster when your initial state is cooler. So in terms of this sort of master equation procedure, we can have an inverse Pemba effect also. Okay. So so in the previous slide, I just mentioned about the discrete space system, but people have looked at continuous space systems also. And this is the experiment that I have briefly indicated before. This is a colloidal system, and they tried to quench the system into a final state. So the colloidal particle is in this kind of a bistable potential, and they try to relax the system for various asymmetries that are shown here. For a symmetric potential, they find that there is no Pemba-like relaxation, but here one can see here that the equilibration time sort of decreases as we increase the initial temperatures and as we increase the asymmetry in the system. And here also we can see whatever we have seen, an exponentially faster relaxation compared to the typical relaxation as we can see. And this was, so the basic idea or sort of an intuitive idea that was there prevalent behind this sort of behavior was related to metastable states here. So if a system is, if the system has multiple minimas, then heating up of a system sort of excites lots of particles that are trapped in the metastable states, allowing the system to approach the lower, what is the final state in a faster manner. But some recent studies that have conducted by people in the audience, like Rajesh sir and Arnab is there. So what they have done is they looked at various systems and found out that actually this metastability itself is not necessary, given that there is certain amount of asymmetry in the system. Which, even for single well potentials, one can get PEMBA like what to say, anomalous relaxation, as we can see in this case. So this is the context that we are in the, what to say, whenever we look at continuous time Langevin systems. And now, now what we wanted to understand is what happens if we do away with the equilibrium systems when we look at non-equilibrium systems, whether we can capture such sort of effects in intrinsically non-equilibrium systems. Okay, so if we want to look at an intrinsically non-equilibrium system, what do we want to do? So we do not have any external, what to say, thermal bath to excite the system. So we will be looking at systems which are driven by certain external forcing, which we don't know a priori, and this driving actually keeps the system in steady states. And now we quench from this particular initial and final state to a new state, which is determined by the new, what to say, a certain different kind of driving, or the driving strength which is different from these two. So that will determine the new final state, and we would like to look at how this evolution can be, whether we can say that one of the evolution which is started with having higher energy or higher magnitude of driving, whether that can be, that can reach the final state in a faster manner compared to other. Is there any such scenario? So the question that we need to have is whether we can have a distance measure for that, and whether with such a distance measure for these two initial and final states, we can indicate a crossing between these two trajectories. Yeah, quench means, say, for example, you have a certain driving with certain magnitude for a similar kind of, two different similar systems. What to say? Yeah, similar means, yeah, two identical systems with two different drivings. And then you, so that sustains these two systems into two different steady states. And then you bring in you bring into these two systems to a different driving strength. So that will relax this system to a particular or a new. Yes, yes. So by quenching, we mean instantaneously you drive the system. So maybe we'll look at one of the models here where you change the driving strength in the kind of for the model of granular gas. Yeah. So we again here also we want to see whether such crossing can be understood here. Okay. So the main difficulty while understanding this in the context of non-equilibrium systems or many particle systems in general is that the distance measures, mainly if we are aiming at this based on probability densities like KL divergence or such measures, or L1 measures for example, then what we need is we need to have information for the entire trajectory of its evolution. It's mostly easy if we typically easier when compared to when we are looking at the single particle evolutions. But if we are looking at many particle evolution or non-equilibrium dynamics, analytically it's quite challenging, or even to get these from experiments or simulations is rather difficult. So what people typically do is to look at moments of these distributions and how does its time evolution capture such anomalous relaxation. So examples may be mean energy per spin or magnetization or granular temperature that we will see, which is the average or energy per particle in the granular system. So these are like the more tractable choices of measures that that can be looked at to capture the evolution of the system. So now, if we are looking at such moments, the question is whether such distance measures obtained from this kind of proxy measures in terms of these moments, whether that are unique or whether these have some correlations with the other distance measures, whether we can take in the PEMBA kind of relaxation that we can obtain using this evolution of these moments, and whether when we compare these with the distance measures obtained from the probability distributions, whether these are sort of related, or whether there is some whether there is no point in looking at these two. So this is the thing that we wanted to consider. This is one of the things. So there are mainly two goals that we were aiming at. One is to look at whether we can have such anomalous relaxation in a formal manner in granular systems, and whether the distance measures that we use there are related to the distance measures that we can look at in terms of probability densities. So that's the aim that we have. And to address this, we look at this prototypical system of granular gas, which is an intrinsically non-equilibrium system. And this system consists of n particles, and these particles are not dense, so they interact via two-particle interaction. And these are, if we don't drive the system, the energy decays monotonically. But now, why? Because the collisions are inelastic, and so the vibrational degrees of freedom sort of like wither away the kinetic energy irreversibly. So what one has to do is to drive the system mechanically or otherwise to keep it in a steady state. So this is one example where suitable external driving can keep the system in a steady state. So this is, so actually we have done certain kind of research in this kind of systems, and so this is sort of a tractable system. So we want to look at this system as an example to ask the questions that we just mentioned before. Okay, so what is the peculiarity of granular gases? So if we drive this kind of system, they don't go into the universal Gaussian distribution function for their velocity distribution in their steady state, but they show certain non-Maxwellianity at the tails. And you can't actually fit to these ones, but okay, if you are in the near elastic limit, one can go to a Maxwellian form, but the tails have basically a stretched exponential form. So people actually use this sort of behavior to first formally look at anomalous relaxation in the context of granular gas by this set of people. And what they did is, as I mentioned in one of these previous slides, they looked at a system which is driven with certain driving strength, as maybe one example is like here. So you are driving with a mechanical energy on this set of particles. So you drive them with certain driving strength, and that will settle this system to a certain steady state corresponding to certain average energy for the system. And you have another identical copy with another vibrational strength. And now you suddenly change the driving strength to another magnitude, and you look at the evolution of these systems. So here T is the granular temperature, which is by which we mean the average energy per particle, or we can say it measures the total energy within the system. And in the steady state, that remains constant. Now, to look at this system, what they considered is the non-Maxwellianity I just mentioned in the previous slide, and here you can see that basically this non-Maxwellianity can be captured by this a set of series called Sonane polynomial approximation, where you have this A2, which is not related to the previous A2, but yeah. So these are coefficients of the Sonane polynomials, and that captures the deviation from the Gaussian, which is given here. So now, if you want to find the evolution of these moments, like the average energy, that gives us a set of coupled equations for the total energy as well as A2, which are related. Now, so these are intrinsically nonlinear couple relations, and how can we analytically go about it is to look at minor difference from the final steady state. So you look at a steady state and you relax the system from a very minor difference from this final state, and in that case you can linearize the system in terms of this matrix form, and this analysis, as we can see in the Markovian analysis, we can obtain a condition for a relaxation where you can have a crossing, and that tells us that okay, for these granular systems also, which is driven by a homogeneous Langevin driving, white noise driving, that a system which is having a higher granular temperature relaxes to the final state in a faster manner compared to the other ones, the ones which are lower. But here, the question was that the condition actually, one of the conditions to satisfy this anomalous relaxation was that this A2 for one of the system should be greater than the other system. That is, a hotter sample should have a A2 which is greater than this A2 in the lower temperature system or the other system. So this is the condition that one should satisfy. But for steady states, we cannot achieve this because the steady states are captured by only by this Sonane polynomial coefficients, which depends only on the coefficient of restitution. So there is no bearing on the driving strength. So if a system is in a steady state, then this A2 here should be only dependent on the intrinsic parameter like coefficient of restitution or the other system parameters. So if the systems are identical, for any steady state, A2 is identical. That tells us immediately that we cannot use or we cannot have any Pemba effect for if we are starting from a steady state. Because in steady state, you cannot have any difference between these two.
So I don't understand. Can you repeat that?
Yeah.
This is the same in equilibrium, the analysis.
No, yeah. So what I meant, you are looking at this point, right?
Yes.
Yeah. So
I don't understand.
yeah. So this A2 here, if you look at the calculations, you can see that it depends only on the coefficient of restitution of the system, which is a system parameter. So whatever be the driving, if you are looking at the steady state, it depends on the system parameter. It's a what to say.
Suppose you take sigma equals 0, the end sigma. Would that also be true?
If these are 0, so
Sigma. So you go to equilibrium, so to speak.
no, yeah. If this is sigma, it goes to a what to say. There's no driving to sustain the system to be in a dynamic state. So you will not go to, so you will not, so it collapses, the system collapses into a what to say, inhomogeneous mixture of particles.
Which still makes sense.
The temperature, yeah. So yeah, that is true. So yeah, there is a time evolution for the energy, and now, but in that case, the thing is that first question is whether this distribution breaks. So this kind of analysis cannot be done in this way because the velocity distribution will become completely.
Whether Pemba or not in this analysis will also depend on sigma. On the final
In this case, yes. Okay. So given that they don't, so we cannot have any steady states from which you can relax the system to and show the Pemba effect. So we looked at other sort of choices of systems where we can have such anomalous relaxation, and one can start from initial steady states. And we looked at one of the immediate examples that we could consider was Maxwell gases, which are basically the granular gases itself, but it is sort of in a mean field clad. That by that we mean is that each particle can interact with any other particle without, what to say, with the same rate. Usually the collision rates are dependent on, in kinetic theory, it depends on the relative velocities of the particles, but one can take that, that collision rate to be independent of their, independent of the relative velocities, so that it simplifies the analysis. So in that way, each particle can see any other particle. Yes. Yeah. Yes, yes.
So, I mean, while reaching there, so you can see that, I mean, they are crossing at some point very early in time.
Here, yes.
Okay, but all the curves should follow the, I mean, at the end, they should be.
It should approach the same steady state finally, yeah.
Okay.
Okay, so yeah, so when we considered Maxwell gases also, there we have certain simplifications in the, so this in Maxwell gases, if you look at this evolution, here the evolution of this temperature, the granular temperature was intrinsically nonlinear, but if we look at Maxwell gases, we have a closure between the second moments, which allows us to get a linear relation for the granular temperature without invoking any, what to say, neighborhood of, or evolution from any neighborhood of equilibrium. You can, so the system, this evolution of temperature, granular temperature in Maxwell gases are basically linear in its construct, and one can do this, the formal analysis that we have done here directly. And here we considered one component, that is single species and two species systems. Even, yeah, both the systems we considered, and we could see that even here we equivalent to this, we have certain conditions which do not allow the system to relax from any steady state and show the Pemba effect. So Pemba effects requires certain conditions which are violated here. So equivalent to this, because you need correlations which are basically 2-point correlations which are not valid for steady states. So one of the next candidates we tried to look at was anisotropic driving. So here, if we look at an equilibrium gas, if you drive, or there is equipartition which allows that, which tells us that the average or the variance of velocities in x component or y component are same, right? There is no difference among the two. But if you look at granular systems, basically you don't have any equipartition that is satisfied. So if we have any driving which is different for x component or y component, this x and y can be different. So, so if you drive system in a different manner in one direction compared to other, basically we have two conjugate variables which we can play around, and using this we can construct total energy in terms of Tx plus Ty, and another conjugate variable T difference in terms of Tx minus Ty. And here also you can have an evolution of these granular temperatures and proceed. So here, in this case, what we did is to look at two driving strengths corresponding to each of the initial states. So there is an x component, driving along x component and driving along y component corresponding to this initial state. And again, here there are two different driving strengths correspond to this Q, initial state Q, and then you finally quench it to a common driving strength, but different along x and y. And this corresponds to similar final states, but yeah, there is an anisotropy in the driving in these final states. So this is the system that we have. And now when we look at this system, so yeah, I'll not go into the details of this calculation, but what we have is that we will have a collision term corresponding to the collision of these particles, and you have driving here, which we take is diffusive driving. And from this evolution, we can, and another approximation that we do is that we do away with the next order correction to the Gaussian. We consider the zeroth order term, which is the Maxwellian form for the function. And that allows us to get a evolution equation for this T total that we saw in the previous slide and T difference. And here we find, okay, as before, we have a nonlinear coupled differential equations. And to, as before, we look at small difference from this initial state so that we can linearize the system to check whether you can have a Pemba-like relaxation. So now we have this sort of linear relations, and that will boil down to looking at crossing of trajectories for this kind of evolution. And we can find the condition for Pemba-like evolution. Like if your initial condition satisfies this condition, then we can have a Pemba-like crossing. That is, you have a finite time at which you have a crossing of trajectories. And yeah, this is one of the subspace of these parameters where you can have regions where you have Pemba effect present and absent. And one can see that as inelasticity vanishes, you have Pemba effect absent, because in the elastic limit you don't have equipartition here. Okay. So finally, I just want to look at another question that we posed in the initial part. That is, here in the previous sort of like exercise, what we found is that we looked at the evolution of the moments of the distribution function and see whether there is a crossing between the trajectories of this evolution. Now, yeah, and so it is better to compare with what to say, look at the evolution of the distribution function itself, or by using certain distance measures, whether we can have a comparison, whether this indicates the evolution of these moments or the existence of Pemba effect in terms of the moment evolution, whether that will that corroborate, or that and the evolution, the Pemba effect in terms of the evolution of the probability distribution functions, whether these are in unison or there is some difference between these two, whether there is a correlation between these two. So for that, what we do is basically we look at the same system, and at the same time we track the velocity distribution in a numerical, from numerical Monte Carlo simulations, and we compare these two. So we have the initial state for a system and a final state for a system, and we quench and we evolve the system, and we look at the moments, which are the energies of these systems, and its evolution as a function of time. And at the same time, we also look at the probability distribution function of these velocities as a function of time from a Monte Carlo simulation, and compare these two, and look at the KL divergence of the probability distributions for the two different systems. Okay, yeah, so we look at various measures. I'll not go into the details. We look at the total energy as we have done before, which is the T total that we saw. And then we look at the other measures which look at based on the moments. And also we compare with KL divergence here, which is given by this definition. And this is the figure that we, or this is the kind of feature that we see for a particular case. And here what we see is that distance measures matter actually when we predict the Pemba effect. So here when we look at these four different evolutions, we can see that in one of these things that we have seen, we have looked at before. Here we see no Pemba effect, but if you look at for the same initial conditions, for the same evolution, if you look at the KL divergence, you can see the Pemba-like evolution for this system. So there is a dependency on the distance measures which we have to consider when we are looking at, when we are trying to claim that when there is a Pemba effect in terms of moment. So there should be a careful consideration that one has to take in here. And here this is the phase diagram that one can construct for these four different distance measures. And one can see that, okay, there are quantitatively these are quite different, and so yeah, so one has to be careful about distance measures that we employ in understanding the Pemba effect, in at least in the granular system. So basically concluding, we considered Pemba effect in the context of granular gases, and we could show that isotropically driven granular gas, when we do a linearized analysis, it does not allow existence of Pemba effect for these systems. But for anisotropic driving, we could show the existence of Pemba effect. And one of the motivations to study these kind of systems is to see whether faster equilibration protocols or faster relaxation protocols can be built for these kind of systems also. And finally, we looked at the various distance measures, and we have to what we found was that when we look at proxy measures, one has to take extreme care to claim the existence of Pemba effect in the Now, so we are at the outlook. We are looking at other proxy measures which can actually be correlated with the probability KL divergence kind of distribution dependent measures of evolution of the system. So so these are the collaborators for this set of works. So okay, thank you.
Thank you. In the case of the equilibrium, you have this intuition that you explained with metastability, or at least asymmetric potential. Is there an intuition of metastability also for the non-equilibrium evolutions?
So far, we have not come up with such a intuitive picture at the moment.
So for the moment, the analysis in non-equilibrium is based on spectral properties, basically.
At the moment.
But there is no intuitive understanding.
But here at least one could say an asymmetry that is built in here is this anisotropy or non-equipartition.
But that's another asymmetry, I think, no? I mean, the asymmetry is in the dynamics, the one that you're talking about, not in I don't know. Is it you think that's a similarity?
That is one thing that immediately occurs to one's mind.
But you cannot imagine the metastability scenario for these granular gases?
At the moment, no.
Thank you.
Questions? So I'm sure there are more questions, but they'll catch up in the tea break.